This ShowMe is about multiplying binomials. You see here by the example I've put in the middle of the page, what we're going to have here is expressions where we have two parentheticals right up next to each other. And we're going to have sums of two terms inside. The first term is usually, but not always, going to be a linear term, ax, and then b, or cx, and then d. It's a very common construction, something we're going to see a lot of as you continue in your basic study of polynomials and factoring. I'm going to give three interpretations of the problem. The first is a geometric interpretation based on the formula for the area of a rectangle, which is, of course, length times width. The second interpretation is simply an application of the very familiar distributive property, but in a relatively unfamiliar way. But everything you needed to know about doing this is already in your skill set if you really understand the distributive property well. Finally, I'm going to show you the interpretation of the distributive property that we use specifically for this application, which makes the process very clean, crisp, and quick, and usually very accurate. So here's the Poliquin art form of a rectangle. I've divided it into parts so that I can relate the parts of this rectangle to the parts of the expression you see in front of you. You see that I'm going to multiply 2x plus 1 times x plus 3. I'm going to treat this like the dimensions of a rectangle, and I'm going to say that the base of the rectangle is x plus 3. If this length is x and this length is 3, then the entire length of the rectangle is x plus 3. In the same way, I'm going to divide up the width. This is going to be x, this is going to be x, and this is going to be 1. So this dimension is 2x plus 1. So you can see that if I could know what the area of the entire rectangle was, I'd have an answer. Well, this can be done. The trick is to divide it up into parts as I've done. Each part is also a rectangle. Its area is found in the same way as the area for the entire rectangle. Multiply length times width. So for the upper left rectangle, which happens to be a square, the length is x, the width is x, and the area is x squared. Below that again, x squared is the area. At the very bottom of that column, the area is 1 times x, which is just x. Back up to the upper right, we have x times 3, which is 3x, and x times 3 again, which is 3x, and finally 1 times 3, which is 3. The area of the entire rectangle is going to be the sum of the areas of each of those regions. So we can rewrite our original problem as x squared plus x squared plus x plus 3x plus 3x plus 3. And then combining like terms, we have two x squared plus 7x plus 3. And so that's a geometric interpretation of the process. There are ways to adapt this so that you can account for negatives, and it works. And if you want to do them all this way, somebody could show you how to do that. It's a bit much work, it takes up a lot of space, and frankly it isn't necessary to go through this entire process. I'm going to show you a much faster way. But this is a good visual interpretation of what you're doing. Often it helps your understanding. I said in the intro that you already have all the knowledge and skills to do this if you understand the distributive property well, and I meant that. Let's see if we can compare this to our distributive property as we understood it before. The original distributive property says A times the quantity B plus C would be AB plus AC. How can I use that here? Well, let's treat the entire expression 2x plus 1 as though it is A. And then x plus 3 would be b plus c. That means that 2x plus 1 would be multiplied by each of the terms inside the second binomial. So we're going to have 2x plus 1 times x plus 2x plus 1 times 3. Then we can use the distributive property again, along with our knowledge of the fact that multiplication is commutative, to say that 2x plus 1 times x has to be x times each of the terms inside of 2x plus 1. So we can take 2x times x and get 2x squared, and 1 times x and get x. In the same way, we can take 2x plus 1 times 3. Each of the terms inside the binomial 2x plus 1 would have to be multiplied by 3. 2x times 3 is 6x, and 1 times 3 is 3. Finally, combine like terms, we get the same answer that we got before. 2x squared plus 7x plus 3. Again, note what we've done. We've used the distributive property twice. The first time, we treated 2x plus 1 as though it were a, and then x as though it were b, and 3 as though it were c, and then behaved accordingly. 2x plus 1 got multiplied by x to give us the first term, and then it got multiplied by 3 to give us the second term. Then we just did it again. We treated x as though it were a, and 2x and 1 as though they were b and c. And x times 2x gave us 2x squared, and x times 1 gave us x. And again, one last time, 3 was treated as though it were a, and then 2x and 1 again were b and c. I took 3 times 2x to get 6x, and 3 times 1 to get 3. After that, it was simply a matter of combining like terms to reproduce the same expression we got in the previous frame. So you see, if you really had a deep understanding of the distributive property, and I got to warn you, you probably don't, but if you did, you could do this. The reason I say you probably don't is that this is a pretty sophisticated idea. The idea that we're going to look at this binomial, something that we're calling a binomial because it combines more than one number in the first place, and we're going to treat it as though it were a single number. That's not an easy mental concept for an Algebra 1 student, a 7th or 8th grader, or 9th grader to get their mind around. But intellectual maturity is now going to be expected of you at certain times. But for this particular application, we decided to dispense with it. And that means there's one more method to show you, and this is the one we're going to use most often. As you can tell by what I have on the screen here, it's likely the name of what I'm about to teach you is the FOIL method, and that's indeed what we call it. It's a mnemonic device. Mnemonic devices use rhythms or sequences of letters, or the spellings of words, or even sentences to give you a way to remember things. Some of the most common mnemonics you'll know would be Holmes or ShowMe for the names of the 5 Great Lakes in North America, or Please excuse my dear Aunt Sally for the order of operations, which we often call PEMDAS. Here we're using FOIL. And FOIL is also an acronym. The first word is first. The second word is outside. The third word is inside. And the final word is last. This gives us a sequence of multiplications that we can do. I assure you we are duplicating both the work we did with the geometric interpretation and the work we did in the previous screen with the distributive property here. It's the same idea, but organized in a way that's easy to remember and quick to execute. So let's do this. When we say first, we mean we're going to multiply the first term of each binomial together. So we have 2x times x, which gives us 2x squared. When we say outside, it means we're going to multiply the terms on the outside of the multiplication as it is written. We're going to multiply 2x times 3, and that gives us 6x. When we say inside, that means we're going to multiply the two numbers that are interior to what we've written. So 1 times x, which is x. Finally, the last term in each binomial, it's multiplied together, and we have 3. If you look closely at each of the previous screens, you'll see that we did exactly those multiplications every single time. So there really is no difference, and we're going to get the right answer, of course. The last step, usually with the FOIL method, is to combine these two terms. Most of the time, but not always, they will be like terms, and you'll need to put them together. That's the FOIL method. It's fast, it's quick, you can repeat it quickly, and this is something you have to learn at a pretty high level. You've got to be able to do this almost automatically. My best students can usually do it in their heads. So let's practice the FOIL method. I like to waste a line on my paper And just write these out so you don't forget, and I recommend that you do that too. For f, f stands for first. The first terms are 4x and 3x. 4x times 3x is 12x squared. The outside terms are 4x and 4. 4x times 4 is 16x. The inside terms are 5 and 3x. 5 times 3x is 15x. And then the last terms in each binomial are 5 and 4. 5 times 4 is 20. Everything here is positive, so there's no need for any subtraction signs. Now we need to combine our like terms in the middle, and we'll be done. So we have 12x squared plus 31x plus 20. That's the product of 4x plus 5 and 3x plus 4. Here we have a little variation, something we haven't dealt with yet, a negative sign. It's easily dealt with. Polynomials are sums of terms. So even though you see a minus there, what's really happening is that we're adding a negative 4. Now that we've taken care of that, we can proceed. Again, please waste a line on your paper to make sure you have everything organized according to the method we've all agreed to use. First terms, 4x times 3x, 12x squared. Outside terms, 4x times negative 4, negative 16x. Inside terms, 5 and 3x give us 15x. And last terms, 5 times negative 4 is negative 20. We're adding all the way, but of course, some of the things we're adding are negative. So when we simplify this for our final answer, it may be that we'll have some subtraction. Well, let's do that. We've got 12x squared. We again have two like terms in the middle. This time, we have negative 16x plus 15x, which is negative x. And then we're adding a negative 20 at the end, so minus 20 will be the final term. So that is the product of 4x plus 5 and 3x minus 4. Notice that the minus sign has a profound effect on both the middle term and the last term. We have the same terms in this product as we had in the previous screen, but that one little negative sign had a pretty profound effect on how the product looks compared to how it looked last time. Finally, let's have a look at how things are when both terms look like they are subtractions. Of course, they aren't really. All polynomials are sums of terms. So this is 4x plus negative 5, and this is 3x plus negative 4. Again, please waste that line on your paper to save yourself some chances to make mistakes. First terms, 4x times 3x is 12x squared. Outside times outside, 4x times negative 4 is negative 16x. Inside terms, negative 5 times 3x, negative 15x. And last terms, negative 5 times negative 4 is positive 20. Again, we're adding all the way, but some of the things we're adding are negative. For our first term, we're still going to have 12x squared. There are no other square terms. We have two like terms in the middle, negative 16x plus negative 15x, which is negative 31x, and then we have plus 20. I hope you can see this process, when repeated, is going to become something that you're very quick and proficient at. It's easily organized, easily managed. Most importantly, it's something that we can actually do backwards. Right now, we're multiplying them together. You would think that multiplying backwards would be called dividing, but in the world of polynomials, multiplying backwards is actually called factoring. And we're going to spend a tremendous amount of time for the rest of this particular unit in my classes on learning how to do this backwards. But of course, you need to understand how to do it forwards before you can undo the process. This is an example, very much like an exercise I've assigned my own students. Perhaps it's one you'll see as well. The exercise is to calculate the area of the region inside the larger rectangle, but excluding the interior rectangle. So the area of all of this is to be calculated, but not this. In other words, we're going to find the area of the big rectangle and subtract from it the area of the little rectangle. So the expression we're to calculate looks like this. The area of a rectangle, of course, is length times width, so we have x plus 8 times x plus 6. Then we're going to subtract the area of the smaller rectangle, which would be x plus 3 times 3x. Well, for the left-hand expression, or for the minuend, we're going to have to use our FOIL method. Burn a line and put in your FOIL abbreviation to make sure you get it right. First terms, x times x, x squared. Outside terms, x times 6, 6x. Inside terms, 8x. Last terms, 48. We're going to subtract from that the product of these two numbers. I'm going to act like I'm multiplying a negative 3x times x plus 3 using the distributive property. So negative 3x times x is negative 3x squared. And negative 3x times 3 is negative 9x. Now I'm going to calculate the final answer by using a combination of like terms. So I have x squared minus 3x squared, which is negative 2x squared. Then 6x plus 8x is 14x, minus 9x is 5x. And then finally, the only constant in the entire expression is 48. So apparently, that's what it would be. Now, it might throw you off a bit to think, well, first of all, look at the diagram. If you think x is a very large number, the diagram makes no sense. This diagram only works if x is 1 or 1.5. So x is a relatively small number compared to the other numbers in the expression. At any rate, this is the expression they're looking for in that exercise. And students have to learn not to let the negative 2x squared part spook them. That first term does dominate when x becomes very large, but we don't know what x is. Absent that knowledge, this might be a perfectly reasonable answer. The larger point is, this is the process you need to follow in performing an exercise like that, and there happens to be one on the assignment I've given my own students, so this is an important hint for them. That's my treatment of the FOIL method. It's very important to remember that the FOIL method is an acronym for first, outside, inside, and last. I think it's also important to remember that this is specifically for multiplying binomials. When it comes time to do multiplications involving trinomials or other kinds of polynomials, you need to revert to the distributive property. But remember the interpretation I gave earlier. You can always treat one of the expressions as though it is itself a single variable, such as the a in the statement of the distributive property. A times the quantity b plus c equals ab plus ac. You can repeat that as many times as you need to. We did it ourselves on the third screen. Until you have completed the process of multiplying each of the terms through. The FOIL method gets that done for binomials very efficiently, very quickly, and since we use binomials to learn about the properties of polynomials a lot in our typical Algebra 1 units here in the U.S., this is an important concept to master early. There are plenty of practice problems available to you in your textbooks. Do a lot of them. Your teacher probably will assign a lot of them anyway. You know that things you need to repeat will have plenty long assignments to make sure that you really are getting the practice you need. Mastering this is crucial to your success in the remainder of the unit about polynomial and factoring, wherever you encounter it in the course.